For decades, the world was told that quantum computers would fail because of noise, because of cold, because of fragile qubits falling apart in microseconds. But that was never the real wall. The real wall was something almost nobody outside a handful of labs was talking about, and Stanford just took a sledgehammer to it. To understand why this matters, you have to go back to the basics of what a computer actually is. Every computer you have ever touched, from the phone in your pocket to the supercomputers that model hurricanes and fold proteins, runs on the same fundamental trick. It stores information as zeros and ones, billions and billions of tiny switches, each one either off or on, nothing in between. String enough of those switches together in the right pattern, and you can represent a photograph, a song, a spreadsheet, a simulation of the entire planet's weather. It is a beautifully simple idea, and it has carried human civilization from room-sized machines that could barely add numbers to devices that fit in your palm and hold more computing power than the systems that sent astronauts to the moon. But there's a category of problem that this simple trick cannot touch. Not because we have not built the switches fast enough, but because the nature of the problem itself grows too quickly for any number of switches to keep up. Think about trying to simulate how a new drug molecule folds and interacts with a protein in the human body. Think about trying to model the exact quantum behavior of electrons inside a new battery material, or trying to break the encryption that protects the world's financial systems. These are not problems where you just need a faster processor. These are problems where the number of possible outcomes explodes so violently that even a computer built from every atom on Earth, running for the age of the universe, would not finish the job. This is where quantum computing enters the story. Instead of using bits that are strictly 0 or strictly 1, a quantum computer uses something called a qubit. A qubit can be 0, it can be 1, or through a strange and genuinely mind-bending property of physics called superposition, it can exist as a combination of both at the same time. Not a fuzzy in-between state, not a guess, but a real mathematical superposition where the particle is, in a very real sense, exploring multiple possibilities simultaneously. Link enough of these qubits together in a state called entanglement, and you get a system that does not just store more information than a classical computer. It processes an exponentially larger space of possibilities all at once. On paper, this sounds like the ultimate cheat code for computation. In practice, it has been one of the most punishing engineering challenges in the history of science. Qubits are almost impossibly fragile. The tiniest vibration, the faintest stray photon, a whisper of heat from the outside world, and the delicate quantum state collapses. This is why so many quantum computers today live inside refrigerators colder than deep space, chilled down to a hair above absolute zero, isolated from every possible disturbance, because the moment that isolation breaks, the calculation is ruined. For years, this fragility, this problem of decoherence and noise, has dominated the public conversation about quantum computing. It is the problem journalists love to write about, because it is dramatic, and because the solutions, like new refrigeration techniques or clever error correction codes, make for satisfying headlines. But ask the physicists actually building these machines what keeps them up at night, and increasingly, you will hear about a different problem entirely. Not how do we keep the qubits stable. That challenge, difficult as it is being chipped away year after year. The problem that has quietly stalled progress toward truly large-scale quantum computers is far less glamorous and far more fundamental. It is the problem of reading the answer back out. Here is the issue. Once you have built your qubits, once you have entangled them, once you have run your calculation, you eventually need to know what the answer is. You need to measure the state of every single qubit and translate that quantum information into something a human or a classical computer downstream can actually use. This sounds like it should be the easy part. It is not. In fact, for years it has been the part that quietly capped how large these systems could grow, even as the raw number of qubits scientists could build kept climbing. To understand just how serious this became, look at what happened in September of 2025. A research team assembled an array of 6,100 qubits, a genuinely staggering technical achievement built from individual neutral atoms, trapped and arranged with extraordinary precision. For a moment, it looked like the field had turned a corner. 6,100 qubits is not a small demonstration chip. It is a machine that starts to approach the scale where quantum computers might actually begin outperforming classical ones on real problems, but then came the part nobody outside the labs was discussing. Building 6,100 qubits is one achievement. Reading all 6,100 of them back out, quickly, accurately, and without one qubit's measurement interfering with its neighbors, is an entirely different and vastly harder problem. The traditional approach to reading a qubit involves shining light on an atom and collecting the tiny burst of photons it emits in response. That burst of light carries the information about whether the qubit ended up as a 0 or a 1. The trouble is that a single atom sitting in open space only emits its photons in a narrow, specific direction, and most of that light simply escapes, scattering off into the surrounding environment before any detector can catch it. Multiply that inefficiency across thousands of atoms and try to read them one at a time, or even a handful at a time, and you start to see the wall. Sequential readout, checking one qubit, then the next, might work for a system with a few dozen qubits. It becomes a crushing bottleneck for a system with thousands, and it becomes almost meaningless for the million-qubit machines the entire field has been chasing for over a decade. It helps to understand why sequential readout becomes such a punishing constraint as a system grows. Picture a control system trying to measure one qubit, wait for the detector to register a clean signal, record the result, and then move on to the next qubit, and the next, cycling through every single one before the fragile quantum state has a chance to decay or drift out of sync with the rest of the system. For a handful of qubits, this is manageable. For dozens, it starts to strain the timing of the whole experiment. For thousands, it becomes almost self-defeating, because by the time you finish reading the last qubit in line, the earlier ones may have already lost the very information you were trying to capture. It is a bit like trying to photograph a fireworks display, one spark at a time, with a camera that can only take a single exposure every few seconds. By the time you get around to capturing spark number 4000, spark number 1 has long since faded from the sky. No amount of patience or careful engineering fixes that kind of problem, because the problem is not a lack of effort, it is a fundamental mismatch between the speed of measurement and the speed at which quantum information disappears. This is exactly why so many teams around the world have spent the last several years searching for a way to break the sequential bottleneck entirely, rather than simply trying to make each individual measurement a little bit faster. Speeding up a single measurement by 10 or 20% does very little when the underlying architecture still forces every qubit to wait in line. What the field actually needed was a fundamentally different approach, one that did not just optimize the Q, but eliminated the Q altogether. This is the wall that Stanford just cracked. The breakthrough, led by physicist John Simon and his colleague Adam Shaw, along with a team of collaborators, was published in the journal Nature in January of 2026, and it approaches the readout problem from an angle that is almost deceptively elegant. Instead of trying to catch stray photons scattered randomly from an atom sitting in open space, the Stanford team built something that sounds almost too simple to be the answer to a decades-old bottleneck. They built a house of mirrors, one for every single atom. Here's how it works. Each atom in the array is placed inside its own tiny optical cavity, a miniature chamber formed by a precise arrangement of curved mirrors. When a photon is emitted by the atom, instead of scattering off in some random direction and being lost forever, it becomes trapped inside this small mirrored chamber, bouncing back and forth in a controlled, predictable path. Traditional cavity designs have existed for years, but they generally rely on the light bouncing between mirrors an enormous number of times to build up a strong interaction between the light and the atom, a technique that becomes brutally difficult to engineer once you try to scale it up to thousands or millions of individual atoms, each needing its own cavity. The Stanford team's innovation was to introduce a microlens into each cavity, a tiny curved piece of optical glass that focuses the light with extraordinary precision directly onto the atom. By tightening that focus, the researchers were able to dramatically increase how efficiently each cavity captures the photon emitted by its atom, cutting down the number of bounces needed from potentially thousands to almost none. In simple terms, instead of hoping a scattered whisper of light eventually finds its way to a detector after ricocheting endlessly around a mirrored box, the microlens grabs that whisper almost immediately and channels it exactly where it needs to go. And here is the part that actually solves the scaling problem. Because every atom has its own dedicated cavity, and every cavity has its own dedicated microlens, the entire array can be read out in parallel, not one atom at a time, not a handful at a time, all of them simultaneously. Imagine trying to listen to thousands of separate whispered conversations happening in the same room, each one a burst of light from a single atom, each one needing to be caught, identified, and recorded before it vanishes. The old approach was like walking around that room with a single microphone, moving from person to person, catching one whisper, then moving on to catch the next, falling further and further behind as the number of whispers multiplied. The new approach gives every single whisperer their own dedicated microphone, wired directly into the system, all recording at exactly the same moment. What used to be an impossible bottleneck becomes a straightforward parallel readout. The team did not just propose this idea on paper. They built it, and they tested it at 2 different scales to prove it actually works. First, they constructed and demonstrated a working array of 40 optical cavities, each one holding a single trapped atom qubit, and showed that the system could read out the state of all 40 atoms with high fidelity all at once. 40 might sound modest compared to the 6,100 qubit array mentioned earlier, but the significance is not in the raw number. It is in the proof of concept. It demonstrates that the fundamental physics of the approach works cleanly at a small scale without the kind of crosstalk or interference between neighboring cavities that might have doomed the idea before it ever got off the ground. That 40-cavity result alone represents years of careful design work, iterating on mirror curvature, alignment tolerances, and the exact positioning of each microlens until the system could reliably trap and read out atom after atom without the kind of drift or misalignment that would have rendered the whole approach useless in a real laboratory setting. Then, to prove the concept could actually scale, the team pushed further and built a larger prototype device containing more than 500 individual cavities. This second device was not necessarily meant to hold 500 fully operational qubits performing complex calculations. Instead, it served as a critical engineering demonstration, proving that the architecture, the microlens design, the mirror alignment, the physical structure needed to support hundreds of these tiny optical chambers packed closely together could actually be manufactured and maintained with the kind of precision quantum computing demands. And if the architecture holds at 500 cavities, the path toward thousands and eventually millions stops looking like science fiction and starts looking like an engineering roadmap. It is worth pausing here to appreciate just how counterintuitive this solution is. For years, the instinct in the field was to assume that scaling readout would require increasingly exotic and complicated nanophotonic engineering, shrinking components down to the scale of computer chips, etching intricate waveguides directly onto silicon, essentially trying to miniaturize the entire optical system down to the atomic level. That approach is being pursued by other teams, and it has its own promise, but the Stanford team took a different route entirely. The resonator, the main body of the cavity system, is not some impossibly tiny nanostructure. It measures roughly 34 centimeters, built at what is essentially a macroscopic, almost hand-sized scale, using a free space optical design stabilized and focused by the microlens array. In other words, they solved a nanoscale physics problem using a solution you could hold in your hands. That combination of simplicity and effectiveness is part of what has other physicists in the field calling this one of the more elegant breakthroughs to come out of quantum optics in years. John Simon, the study's senior author and a physicist at Stanford, summed up the motivation behind the entire project in a single, deceptively simple sentence. If you want to build a quantum computer, you need to be able to read information out of the qubits very quickly. It sounds obvious when you say it out loud, but it captures exactly why this unglamorous, unsexy corner of quantum engineering ended up being the thing standing between the field and its next major leap forward. You can build the most sophisticated array of entangled qubits the world has ever seen, but if you cannot extract the answer from that array fast enough, accurately enough, and at large enough scale, the calculation might as well not have happened at all. So why does any of this actually matter beyond the walls of a physics lab? Because the promise of quantum computing was never really about faster spreadsheets or quicker video rendering. Classical computers are already extraordinarily good at the tasks. Most of us use computers for every single day, and quantum computers are not going to replace your laptop or your phone. The real promise lies in an entirely different category of problem, the kind that grows exponentially harder as it gets bigger, the kind where classical computers, no matter how powerful, eventually hit a mathematical wall they simply cannot climb over. Consider drug discovery. When researchers try to design a new medication, one of the central challenges is predicting how a candidate molecule will interact with the complex three-dimensional structure of proteins in the human body. The number of possible molecular configurations and interactions is so vast that classical computers can only approximate the answer, running massive simulations that still fall short of full accuracy, and that can take months or years to complete. A sufficiently powerful quantum computer, one that can actually read out its results reliably at scale, could simulate these molecular interactions far more precisely, potentially compressing years of laboratory trial and error into a fraction of the time, or consider materials science. Every battery, every solar panel, every superconductor humanity has ever built is, at its core, a story about how electrons behave inside a material. Predicting that behavior from first principles, using the actual laws of quantum mechanics rather than simplified approximations, is exactly the kind of problem quantum computers were built for, and exactly the kind of problem classical computers struggle to handle as the materials grow more complex. A breakthrough in quantum readout brings the field closer to designing next-generation batteries, more efficient solar cells, and entirely new classes of materials that do not yet exist. Then there is the world of cryptography and secure communication, an area that tends to generate as much anxiety as excitement. Much of the encryption protecting the modern financial system, private communications, and government secrets relies on mathematical problems that are, for classical computers, essentially impossible to solve within a human lifetime. A sufficiently powerful and scalable quantum computer changes that equation, which is precisely why governments and research institutions around the world are pouring resources into both quantum computing and the next generation of quantum-resistant encryption designed to stay ahead of it. And increasingly, there's a connection between this kind of breakthrough and the world of artificial intelligence. Some of the most computationally expensive tasks in modern machine learning involve searching enormous, high-dimensional spaces for optimal solutions, whether that is training massive neural networks or solving complex optimization problems that show up in logistics, finance, and scientific research. Quantum computers, once they reach sufficient scale and reliability, are expected to offer meaningful advantages in specific corners of this landscape, working alongside classical AI systems rather than replacing them outright. Even fields that seem far removed from physics stand to benefit. Climate modeling depends on simulating enormously complex systems, from ocean currents to atmospheric chemistry, where classical computers are forced to rely on simplifications and approximations simply because the true physics involves an overwhelming number of interacting variables. A sufficiently powerful quantum computer could, in principle, model these systems with a level of fidelity classical machines cannot approach, offering sharper predictions about everything from extreme weather events to long-term climate trends. Financial modeling faces a similar story, where portfolio optimization and risk analysis involve searching through combinatorial possibilities that grow explosively as the number of assets and variables increases, exactly the kind of landscape where quantum algorithms are expected to eventually offer a genuine edge over classical techniques. None of these applications become possible with a quantum computer that can only reliably operate a few dozen qubits. They require systems that can scale into the thousands and eventually the millions, while still being able to read out their results quickly and accurately. That is exactly the gap this Stanford breakthrough targets. It does not, on its own, deliver a million-qubit quantum computer tomorrow. Nobody involved in the research is claiming that. But it removes one of the most stubborn obstacles standing between where the field is today and where it needs to go. It is also worth being honest about what this breakthrough does not solve. Scaling qubit readout is a critical piece of the puzzle, but it is not the only piece. Error. Correction remains an enormous ongoing challenge, since even a small error rate per qubit compounds dramatically once you're operating thousands or millions of them together. Maintaining coherence, keeping those fragile quantum states intact long enough to actually perform a useful calculation, remains an active area of research, with teams around the world pursuing everything from better isolation techniques to faster, more efficient error correction codes. And the engineering challenge of actually manufacturing and aligning a million individual optical cavities, each one precisely tuned to trap a single atom, is not something that happens overnight, even with a proven architecture in hand. But that is how science actually progresses. Not through a single dramatic breakthrough that solves everything at once, but through a series of stubborn, unglamorous walls being identified, studied, and eventually knocked down, one at a time, by researchers willing to spend years focused on a problem most people never even knew existed. The public conversation around quantum computing has spent years fixated on cold and noise, and rightly so. Those are real and serious challenges. But the researchers actually building these machines have been quietly wrestling with readout the entire time, aware that even a perfectly stable, perfectly entangled array of qubits is useless if you cannot get the answer back out fast enough to matter. What makes the Stanford result particularly compelling is not just that it solves the problem, but how directly it does so. There is no exotic new material involved, no radical rewriting of quantum theory, no speculative leap that requires years of additional validation before anyone can trust it. It is a clever, careful piece of optical engineering, built on decades of established cavity physics, refined with a microlens that focuses light more precisely than previous designs allowed. It was tested at 2 different scales, demonstrated to work reliably, and published through the rigorous peer review process required by one of the most respected scientific journals in the world. That combination of elegance and rigor is exactly why physicists outside the research team have taken notice, and why a discovery about something as seemingly narrow as optical cavity design is being discussed as a genuine turning point for the field. Where does this leave quantum computing as a whole? Still early, still years, likely, from delivering on its most transformative promises. Building a truly practical, error-corrected, million-qubit quantum computer remains one of the most difficult engineering challenges human beings have ever attempted, and no single breakthrough, however elegant, changes that overnight. But science rarely advances through single leaps. It advances through exactly this kind of moment, a stubborn, overlooked bottleneck finally giving way, opening a clear, incredible path where before there was only a wall. For years, the qubits themselves got all the attention, celebrated every time a new record was set for how many could be assembled into a single working array. Meanwhile, the unglamorous problem of listening to what those qubits were actually saying, of extracting a usable answer from thousands of simultaneously vibrating quantum whispers, sat quietly in the background, largely unnoticed outside a small community of specialists who understood exactly how much it mattered. Stanford's House of Mirrors changes that equation. It takes what was once one of the most stubborn, least discussed obstacles in quantum computing and turns it into a solved engineering problem, backed by working hardware, peer-reviewed results, and a credible path toward the kind of scale the entire field has been chasing for more than a decade. The road to a million-qubit quantum computer is still long, and there are still real difficult challenges ahead. But for the first time, the path forward looks less like a wall and more like a series of steps, each one a little more achievable than it seemed a year ago. And that shift, from an impossible barrier to a solvable engineering challenge, might end up being remembered as one of the quiet turning points that made the next generation of quantum computing actually possible. It is worth remembering that breakthroughs like this rarely announce themselves with the fanfare the underlying achievement actually deserves. There was no dramatic press conference, no sweeping declaration that quantum computing had suddenly arrived. Instead, there was a research paper, carefully reviewed, quietly published, describing 40 cavities and 500 more, each one holding a single atom, each one proving a little more of the same elegant idea. That is how most of the real progress in science actually happens, not in a single blinding flash, but in the patient accumulation of solved problems, each one clearing the way for the next. And perhaps that is the most important lesson buried inside this story. The obstacles that end up defining an entire field are not always the ones that make headlines. For years, the loudest conversations about quantum computing centered on cold and noise, because those problems are easy to visualize and dramatic to describe. But the researchers actually building these machines were focused on something quieter, a bottleneck in how information gets read out of a system, a problem so unglamorous that most people outside the field had never even heard of it. And yet it was precisely that unglamorous problem standing between the quantum computers of today and the quantum computers the world has been promised for over a decade. Stanford's House of Mirrors did not just solve an engineering puzzle, it reframed what the biggest obstacle in quantum computing actually was, and in doing so, it handed the entire field a clearer, more credible map toward the future everyone has been waiting for.